Hi everyone, welcome to part 3 on our video lecture for section 12.3 on the calculus in polar coordinates. In the previous video, we were going over how to find points of intersection for polar curves and how to determine the area of a region bounded by a polar graph. In this video, we're going to continue on with more examples on how to find the area for a region bounded by a polar graph, and then we're going to see if we can find the area that is bounded by two polar curves. So let's go ahead and begin here with example 5. And we're trying to find out the area for the region enclosed by the inner loop of a limacon given by the equation r equals to 1 minus 2 cosine theta. Alright, so as usual, let's go ahead and begin by making a graph of the polar curve to know what we're dealing with. So we have our limacon was given by 1 minus 2 cosine theta. So let's see, what should we expect? Well, there we go. And now at this point here, careful, I did not change my window settings. So I do want to trace the whole thing, so I'm just going to go here from 0 to 2 pi and change the window here to assume fit. And there we go. Now we have our limacon with one inner loop. And we want to figure out what is the area underneath, or what's the area for this inner loop. Alright, so once more, I'm going to go ahead and attach an image for our polar curve, but you guys should be making a sketch. Because again, remember, we do want to figure out, okay, what may be some possible points of intersection, or what are going to be the desired angles that we're going to be looking for. All right, so let's see. Here's my curve, and we're looking for the area for this inner loop. So that means that we're basically looking for what are going to be the angles that form this inner loop. Now, one thing that I notice here is that this inner loop seems to be forming as you're crossing the pole. So I want to figure out, okay, well, what is that value? So that means that we need to set here our equation equals to 0. So I'm going to go ahead and do that. We're going to have 1 minus 2 cosine theta equal to 0. Now this is just going to give us here a cosine of theta equals to 1/2. Okay, so now let's see what's going to be the angle that gives you a cosine value of 1/2. Now once more, since the limacon was traced as theta went from 0 to 2 pi, we're only focusing on angles that are between 0 and 2 pi, and the angles that give you a cosine value of 1/2 are going to be theta equals to pi over 3 and theta equals to 5 pi over 3. Okay, so let's go to our graphing calculator and see where those values are. So I'm going to go ahead and begin with the with the angle of pi over 3. So let's see, trace second pi over 3. And there we go. It looks like we are indeed at the pole. Now what happens here though, if I try the 5 pi over 3, yeah, it's the same thing. It's going to be giving us the result at the pole, which is good. So let's see, I'm going to go ahead and click on window and say that, okay, there's a good chance that the inner loop is going to be traced from pi over 3 to 5 pi over 3. So let's take a look. Let's begin here at our x min of pi over 3. So second pi, oops. Clear this. So second pi over 3, and let's end at the 5 pi over 3. So 5 pi over 3, and let's see what's being traced. Uh-oh, wait, what's happening here? We lost the loop. Okay, so something went awry. So what can we do then? It seems like the angles are not going from pi over 3 to 5 pi over 3. So what else can we do? And we're seeing here that, oh yeah, well, polar equations can be tricky. All right, guys, so let me just point it here. There you go. The loop is not formed on the values for theta that are greater than or equal to pi over 3 and less than or equal to 5 pi over 3. So here's what we can do. Always ask yourself, well, where is the curve starting? Very similar to the parametric equations. Where is your starting point and where is your direction? So let's see. I'll just put here, where is theta equal to 0? So I'm going to go here to my calculator and just begin here at, and still going from 0 to 2 pi to get the full shape. There we go, graph it here. All right, now I'm going to go ahead and click on trace and see when the angle is 0, where are you? Okay, so it looks like when the angle is 0, you're starting right here. So I'll just put here theta is equals to 0. Now here's the good news though. We just said right now that when theta was equals to pi over 3, you ended up here at the pole. So it looks like if you wanted to trace part of the inner loop, you need to go from 0 to a theta value of pi over 3. So let's see if we do that. We're going to go here to window, start at 0, but now go all the way till pi over 3. Okay, so it looks like we're tracing the bottom half of the limacon. So now we can get an idea of what the curve is doing. So if we start at theta equal to 0, then we're going to be tracing here the bottom half till pi over 3. Then we're going to continue on with the trajectory, and I'll put arrows here. Then it's going to loop around here and go back to the same value for theta equal to 0. So this is our direction. Now at this point, there's different things that we can do. Now let me just put here at theta equal to 0. The R value seems to be, I'll put it here. I'll put it in purple. The the R value seems to be a -1. Okay. Now, what can we do here? Well, there's two different approaches. Now, we can either say that if we wanted to figure out the area for the inner loop, we just said right now that if we set up the integral from 0 to pi over 3, we'd be tracing the bottom half. And I'll call this bottom half here a1. So we can set up the integral here. The area is going to be 1/2 times the integral from 0 to pi over 3 for our radius squared, or r squared. So 1 minus 2 cosine theta, d theta. And it's not the radius. It's a habit for me to say radius, but it's just r. And it's r squared. Okay. Now, the thing here, though, is that this one is only giving us half of the area that we're looking for. It's only giving us a 1, but what about the top half? Well, since these regions are symmetric, if you wanted to figure out a2, well, a2 is the same thing as a1. So what we could do here is say, okay, well, we can just figure out the area for the lower half, the bottom half, and simply multiply it by 2. And that would give you the area of the inner loop. Put here area for the inner loop. Now, another thing that you can do if you do not want to use symmetry, you can still set up two different integrals. Now, the thing that we would need to do to figure out those two integrals is the following. I'm just going to put here, or we could set up the area, or the integral that gives us the area for the bottom half, which we were going from, and I'm going to focus here only on the inner loop. As we went from 0 to pi over 3, we're tracing this. Now, what would be the desired angles so that we could trace the upper half of the inner loop? Well, as we were seeing here with the drawing, as we were following the directions, once we got to the R value of 1 here, or I'm sorry, -1, this theta value is also 2 pi, because you're completing the full cycle here. So what we can do here is to figure out this top half. We can just say here, okay, well, I know that I'm going to reach the 2 pi here, but I can go ahead and subtract a pi over 3. So we can have 2 pi minus pi over 3, and this one here is going to give us 5 pi over 3. And this one here is this value here, which again coincides here with the intersection that we got here at the pole. So basically we would know that if we wanted to get the missing part, we can go from 5 pi over 3 all the way to 2 pi. And I'm going to show you guys here on the graph. Right now, the angle going from 0 to pi over 3 is tracing the bottom half of the inner loop. But if I change my window and now instead go from 5 pi over 3 to 2 pi, I should be tracing the upper half. And there we go. So what we can do here is set up two integrals. The first one being the one that's giving you the inner loop. So it's going to be 1/2 from 0 to pi over 3 for 1 minus 2 cosine theta squared, d theta, plus 1/2, now it's the integral from 5 pi over 3 to 2 pi for 1 minus 2 cosine theta squared d theta. Both approaches are the same thing. However, why do two integrals when we could just easily do one of them and simply multiply it by 2? And that's the approach that I'm going to be taking. Now for this one here, for this integral, we would still need to FOIL it out, but I'm just going to go ahead and cancel the 2's here. So we're going to have here the integral from 0 to pi over 3 for FOILing things out here, we're going to get a 1 minus 4 cosine theta plus 4 cosine squared theta d theta. And now at this point, guys, I'm not going to continue this integral. I just want to focus on the setup. So this one here is going to give us approximately, well, actually, I'll go for the exact answer. The exact answer that we should be getting should be 3 minus 3 rad 3 over 2. So this is the area for the inner loop. Now, again, I'll ask you guys to verify this one, because for this problems, I just want to focus more on the setup rather than the integrals. Okay, so hopefully this one here, it's emphasizing the importance of using your calculator to double check what are the correct angles that are giving us the desired area or the desired trace of the curve. Okay, now, before we go on to the next topic, which will be finding the area that is bounded between two polar curves, I want to show you an animation to give you a better intuition of what we're doing right now when we're calculating the areas. Alright, so here we have our graph for our limison given by the polar equation 1 minus 2 cosine theta. Now, since we're trying to find out what is the area for the inner loop, we said here that if we wanted to get the bottom half of the inner loop, we needed to go from the angles between 0 and pi over 3. Alright, so what I'm going to be doing here is showing you how we can get approximations for the area by essentially drawing or tracing or sweeping an area as the angle changes. And I'm going to go here for the midsum, which is the midpoint equivalent for the Riemann sum. And we get to see here, okay, with one sector of the circle, we are getting this area, which is not too good. But what if we start sweeping or sweep more area by doing more sectors here? So going for 4 sectors, or 3 right here, 4, 5, well, it's going by 2s, but you get to see here that as I increase my number of slices or wedges, you do get a much better approximation of the area here. So going all the way to, I don't know, how far does it go? It'll go 100, it's pretty good. So you get to see here that, yeah, we pretty much got the area. Now again, the important thing that I want to emphasize is that we're not using rectangle. Instead, we're using wedges, and these wedges have an area that is given by the formula 1/2 times r squared times theta. So there we go. Alright guys, so I'm going to leave you with this, and I'm going to go ahead and use this idea of finding an area by sweeping a particular sector to, and apply it to basically finding the areas that's between two polar curves. But I think I'm going to do it here in a separate part of the video, so I'll see you guys there. Part 4, we'll be discussing how to find areas between two polar curves.